Wilson's theorem is one of the most fascinating results in elementary number theory. It's useful for American math competitions, IOQM, ISI-CMI entrances, so we will talk about it. My name is Ashwini Dashgupta. I'm a faculty at chinta.com. You can find more about us in the links in the description. So let's talk about the main underlying concept of Wilson's theorem. Suppose you have a number n such that n minus 1 factorial plus 1 is divisible by n. What can you say about this number then? What can you say about n? So let's check by experiment what happens if we plug in n equals to 4. So 4 minus 1 factorial plus 1. This is simply 3 factorial plus 1. Now what is 3 factorial? 3 factorial is 1 times 2 times 3, which is 6 plus 1. So 7. We get the number 7. And surely 7 is not divisible by 4. Remember, we started with 4 as our n. So this does not work for n equal to 4. This n minus 1 factorial plus 1, this thing does not work for n equal to 4. Let's check if it works for n equals to 5. So we want to check if 5 minus 1 factorial plus 1 is divisible by 5. So how can we check this? Well, let's calculate. So this is 4 factorial plus 1. What is 4 factorial? 4 factorial is 1 times 2 times 3 times 4, which is, this is 4 times 3 is 12. 12 times 2 is 24. So this is 24. So plus 1 is 25. And indeed, 25 is divisible by 5. So yes, it works for n equal to 5. No, it did not work for n equal to 4. So this in fact tells us what the Wilson's theorem is about. It tells us that the claim is n minus 1 factorial plus 1 is divisible by n if and only if n is a prime number. N is a prime number. And in this particular video, I will discuss how you can prove this fact. So there are a variety of ways of proving this, but it's an interesting exercise to prove it using elementary tools. So when I say if and only if n is a prime, this works. Then I have to actually prove two things. First, I have to show if n is not prime, then it does not work. And then I have to show if n is prime, then it works. So really I have to show these two things. Let's first take the case where n is not prime. So n is not prime means n is composite. N is composite means that n can be written as a product of two numbers, a and b, such that A is less than n and not 1, and B is also less than n and not 1. So I can always break down composite numbers into product of smaller numbers which are not 1. Now let's look at the expression n minus 1 factorial plus 1. Now what is this? I want to show that n does not divide this quantity. That's what I want to show. Remember, I want to show that it only works when n is a prime number. In this case, n is a composite number, so I want to show it does not work. It does not divide this. So how am I going to show it? Well, notice that A and B both are smaller than n. A and B both are smaller than n. So in particular, A is smaller than n. So there is a number A in the product from A to 1 to n minus 1. N minus 1 factorial, if you expand it out, A will be somewhere in between. It could be n minus 1 itself. Well, it can't be actually n minus 1 itself, but anyway, it will be a number between 1 and n minus 1. Now, this quantity is divisible by A. This is divisible by A. So clearly this quantity plus 1 is not divisible by A. For example, if 3 divides 12, which it clearly does, then 3 will not divide 13, one more than the number 12. So if A does not divide, n minus 1 factorial plus 1, then clearly n does not divide n minus 1 factorial plus 1, because if n divided this, then all factors of n would also divide this, right? And A is a factor of n, and we just showed A does not divide n minus 1 factorial plus 1. So that shows what we wanted to show, that if n is a composite number, it does not work, or n does not divide this given quantity. So the first case is done. This one is done. Now what we want to check, if n is a prime, then it would work. So let's try that. Case 2. If n is a prime, then it works. But how do we show this? Alright, so the first thing to realize is that there is something called inverse of a number. So what is inverse of a number? Well, given a number A, another number B is called its inverse. These two are inverses of each other. If A times B produces remainder 1 when divided by n. A times B produces remainder 1 when divided by n. So I'll give you an example. Here is an example. Let's take the number n equal to 15. Then what is the inverse of the number 2? Well, the inverse of the number 2 is, one of them is 8. If we just look at numbers less than 15, and if we search for the inverses, then we readily notice that 8 is a number which works, because 2 times 8 is 16. And when you divide it by 15, remainder is 1. The thing to understand is that an inverse can be the same number, can be self. For example, if you take the number 4, the inverse of 4 is 4 itself again, because again 4 times 4 is 16, and if you divide it by 15, remainder is 1. So here is a challenge question. What is the inverse of 7? Again, our reference number n is still 15. So let me ask you a question. If n is a prime number and if we look at numbers smaller than it, then which numbers can be self-inverses? For n equal to 15, 4 was a self-inverse, but 15 is not a prime number. So if we work with prime numbers, let's say n equals to 17, which numbers smaller than 17 can be self-inverses? Well, suppose a is such a number. That means a is a self-inverse. So a times a produces remainder 1 when divided by 17. So a square minus 1, this is divisible by 17. A square minus 1 is divisible by 17. Okay, so this implies a plus 1 times a minus 1 is divisible by 17. But notice that 17 is a prime number, right? So if 17 divides a plus 1 times a minus 1, this product, then 17 would divide either a plus 1 or a minus 1. So how can 17 divide? 17 divides a plus 1 or 17 divides a minus 1. Remember, a is smaller than 17, right? We are only looking at numbers, positive numbers, smaller than 17. So how can it happen that the prime number 17 divides a plus 1? If a is less than 17, that can only happen if a is equal to 16, that is 1 less than the prime number. This is the p minus 1 case. So a is equal to p minus 1. Or if 17 divides a minus 1, then the only case that's possible if a is equal to 1, because then you have 1 minus 1, which is 0, and obviously 17 divides 0. So the second case is that a is equal to 1. So there are only two cases which are self-inverses. So what we just proved, though we use 17, but the argument will be the same for any prime number. We just proved that if n is equal to a prime number, only 1 and n minus 1 are self-inverses. All other numbers are not self-inverses. Now there is something else to be shown. There is a second claim that every number smaller than the prime number has an inverse. How do we show that? Well, first notice that this is not true for 15. This is not true if n is not prime. For example, if n is equal to 15, the number 6 has no inverse. Can you prove this? This is a challenge again. You can try it in the comment section. Prove that 6 has no inverse if the number n is 15. Okay. So, but if it is a prime number, then all the numbers smaller than it will have an inverse. Well, how do we show that? Well, there are multiple ways of showing it, but the most important and interesting way is like this, that let's list out all the numbers 1, 2 up to p minus 1, and suppose I am trying to see if a number k in this list, does this have an inverse? Is there an inverse of k? An inverse of k. So let's multiply each number with k. Let's multiply each number with k, and let's calculate the remainder when divided by p. So k times 1 divided by p, what is the remainder? Let's calculate that. K times 2 divided by p, what is the remainder? Like this, up to k times p minus 1 divided by p, what is the remainder? My claim is no two of these remainders will be the same. Okay, so why not? Suppose, okay, why not? Let's run the argument. Suppose 3 times k and 10 times k produce the same remainder. When divided by the prime p. And I still have the number 17 in my mind. Okay, you can run this argument for any prime number actually. So can this happen? Well, if they produce the same remainder, that is 10 times k is equal to 17 times some quotient plus remainder, and 3 times k is 17 times some other quotient plus the same remainder, then if you subtract it, you'll get 7 times k equal to 17 times q1 minus q2, as these two remainders will cancel off, which basically means that 17 divides 7 times k. But that's not impossible. Why? This is impossible because both 7 and 17 and k are smaller than 17. And 17 is a prime number. Since both 7 and k are smaller than 17 and 17 is a prime number, therefore product of 7 and k cannot be divisible by 17. I just used actual numbers to make the argument simpler for you, but you can run it with pure algebraic letters and the argument will be exactly the same. So what we just showed is that all of these question marks will be distinct. But there are p minus 1 such question marks, right? And I'm dividing by p, so the remainders can be, well, they have to come from the set 1 to p minus 1. Because if I divide any number by p, the remainder is either 1 or 2 or up to p minus 1. Of course, it can be 0, but none of these are divisible by p, so the remainder is not 0. So, among this list of question marks, since all of them are distinct, and there are p minus 1 of them, and there are p minus 1 possible of them, therefore, 1 must appear in this list. This is a subtle argument. Think about it. There are p minus 1 question marks and they can have p minus 1 distinct possible values, and we have proved that all of them are distinct. So there is somewhere in this list 1, right? Because 1 is one of the possible remainders and you have to use up all possible remainders because all the question marks are distinct. So, suppose k times j produces remainder 1, then k and j are inverses of each other. Excellent. So we just proved that, first thing we proved is that only 1 and p minus 1 are self-inverses. And we secondly proved that all other numbers have inverses in the same set. Same set means the numbers from 1 to p minus 1. So I can now pair these up. I can pair this up. So for example, I can pair 2 with its inverse j, whatever, there is some number j here, which is the inverse of 2. Like this, right? Except for 1 and p minus 1, which I cannot pair up because they are self-inverses. So, since p is odd, assuming that the prime is greater than 2, since p is odd, therefore p minus 1, there are even number of things, even number of numbers, and these two, if you leave them out, you still have an even number of numbers. even number of numbers, and each of them we can make pairs like this. For each of them we can make pairs like this. So for example, we can make A1 times B1, A1, B1 both coming from the numbers 2 to P minus 2. I'm just leaving out 1 and P minus 1 for the moment. A1 and B1 comes from this list. Similarly, A2 and B2 comes from this list, and all of them produce remainder 1. This product produces remainder 1 when divided by P. So you can just pair them up to, let's say, AK and BK. Actually, you can actually write down how many pairs will be there. There will be P minus 2 over 2 pairs, right? Because there are, if you leave actually P minus 3 by 2 pairs. Because from the list of P minus 1 numbers, you throw away 1 and P minus 1. So there are P minus 3 numbers left, and you have to divide it by 2 to find the number of pairs. And each of them produces remainder 1. 1 itself, when divided by P, produces remainder 1. And P minus 1, when divided by P, produces remainder negative 1. Now, if you are not familiar with negative remainders, let me remind you that any number A, when divided by some divisor D, produces a quotient and a remainder, right? And you can write A as the divisor times the quotient plus remainder. This is sometimes called the division algorithm. Now notice you can write P minus 1 as 0 times P plus negative 1. So you can think of the remainder as negative 1. So the remainder when P minus 1 is divided by P is negative 1. Now what we are going to do is that we are going to multiply all of these numbers out. If I multiply all of these out, then we will get, this is P minus 1 factorial. If I multiply all of these out, these two are the numbers from 2 to P minus 2. This is 1 and P minus 1. So together they make P minus 1 factorial. And we know, if you don't know this, then maybe I can derive it for you. If a number A produces remainder 1 when divided by a divisor, and number B produces 1 or minus 1 or minus 1 actually, both will work, when divided by a divisor, then if you multiply them and divide it by D, then the remainder will be also the product of the remainders. Product of the remainders. Why is that? Why can you just multiply numbers and divide it to get the product of the remainders in this particular case? Well, let's quickly prove this. Let's suppose A produces remainder 1 when divided by D, it produces remainder 1, and B produces remainder 1 when divided by D. We want to check what happens when A times B produces, when A times B is divided by D. So A produces remainder 1 means A equals to D times some quotient 1 plus 1. And B similarly is D times some quotient 2 plus 1. Let's multiply A times B. So you get dq1 plus 1 times dq2 plus 1. This is equal to d square q1 q2 plus dq1 plus dq2 plus 1 into 1 is 1. So now you can write A times B as d times dq1 q2 plus q1 plus q2 and plus 1. So clearly you can see that this is the new quotient, and this is the new remainder. And you can check this if one of the produced remainder is minus 1. The same argument would work. So now we are absolutely done, because if we multiply all of these out, we can multiply the remainders, but 1 times 1 times 1 a bunch of times and then times minus 1 will just give you this product is product of remainders is minus 1, which means that when p minus 1 factorial is divided by p, the remainder is minus 1. In other words, p minus 1 factorial is equals to p times some quotient minus 1, which is the remainder. Or you can just take the minus 1 to the other side and get p minus 1 factorial plus 1 is equal to p times the quotient, which means that p divides p minus 1 factorial plus 1. Now those of you who know modular arithmetic, this entire argument can be obviously simplified, much more simplified. But I did not want to use modular arithmetic because I want everyone who knows a little bit of addition, multiplication, subtraction and division to follow what I just did. It's very important to simplify a complex idea as much as you can. This is sometimes known as the Feynman technique, that if you can simplify it sufficiently, you will gain a very interesting understanding. I hope you liked it. This was the Wilson's theorem in the simplest term possible. If you like it, you can share and subscribe and comment. Thank you everyone for joining in today. I'll see you in the next one.